So last class we left off talking about electrolyte solutions. Gatorade famously, lots of electrolytes, just means that it has lots of ions in it, and the ions that are in Gatorade and other sports drinks like Powerade and G Fuel maybe are designed, it's like a blend for your body, the things that your body needs to run. It's not just random electrolytes. There are just random electrolytes, any dissolved ions, they'll conduct electricity. So Gatorade probably conducts electricity really well. Our regular drinking water has electrolytes and like dissolved solids in it that we also need. So it's good to drink normal water and not to drink pure water. Pure water would do bad stuff, potentially. Some things that dissolve in water include silver nitrate. A silver nitrate solution, silver being Ag, nitrate being NO3, doesn't contain any silver nitrate units. Silver nitrate is a strong electrolyte, and when it's in solution, it's a strong electrolyte solution. Generally speaking, polyatomic ions like oxyanions stay intact. So they'll dissolve and they stay intact, meaning they stay in one piece. So if we had nitrate NO3 in our formula unit, we also have NO3 but with a minus. When it dissolves in solution, the NO3 isn't getting broken down into nitrogen and oxygen. Just as a general rule of thumb. And we also know that there's water molecules around the silver, there's water molecules around the nitrate. Silver chloride, on the other hand, does not dissolve, or at least does not dissolve much in water. So not all ionic compounds dissolve in water. Silver chloride, that's here. Silver chloride stays as mostly just solid silver chloride when it's put in liquid water. The AgCl attraction, it's not really a bond. That AgCl attraction is stronger than water and Ag/Cl. So it's staying intact because the silver and the chloride really like each other, just maybe because it's their size, maybe it's because of the charges. And so if water comes along and tries to pull off a silver or a chloride, it is simply just not strong enough, it's not sticky enough to pull those silvers or those chlorides off. So it doesn't dissolve into independent ions. So this sort of brings us into solutions and solubility. An aqueous solution, we've talked about before, is a homogeneous mixture, a smooth consistency, evenly distributed throughout mixture of a substance with water. When our ionic compounds dissolve in water, when they dissolve in water, if they dissolve in water, they'll usually dissociate into component ions. The polyatomic ions will stay intact. For example, you can dissolve sodium chloride in water by stirring table salt into a glass of water. Visibly, we don't see it anymore, but we know that it's there if we taste the water. Or if you have enough salts dissolved, you can feel it. It feels like a little bit slimy, sticky. Not sticky, but slimy. We call a compound soluble if it dissolves in that liquid. So like sodium chloride dissolves in water. And a compound is insoluble if it does not dissolve in liquid. The in here meaning not soluble. So that would be like the AgCl, the silver chloride, in H2O. This also applies to liquids and other solids. Like if you just put a chunk of iron, metal, or stainless steel into some water, it just stays intact. It doesn't dissolve into the water, so those would be insoluble as well. For ionic compounds, we have empirical rules of solubility. These are on the green sheet. So we are finally getting around to using that section from the green sheet. There is also a version in the online book that you can use as well. But I will generally be referring to things by the green sheet version, since you should all have a handout of that. You do not need to memorize solubility table stuff. You should know how to use the solubility table. You will be expected to know how to use the solubility table. So you will need to know how to read/use a solubility table. You don't have to have it memorized. Some of the things you might pick up as you use them, that's fine, but don't commit any extra time or memory resources to memorizing a solubility table. Here's the solubility rules that we have from the online book. And this is also generally how solubility tables are laid out. Our green sheet one is laid out the same way, or a similar way. There's two sections. This top section is soluble in water. So if it shows up there, it is soluble in water. So all of these things are soluble, except if they're paired up with something in the exception table. Our green sheet solubility table is the same way. We've got the top groups or ions on the left. If you find any of those are generally soluble. You would then go and look if we have any of the exceptions. If you have one of the exceptions, then it is not soluble. And then the bottom section, here it says on the online book, sparingly soluble. You can basically read that as not soluble. So things that are insoluble, unless we've got one of our exceptions. So if we've got an exception for this top group, it's insoluble. If we've got any of these exceptions, in the bottom, then it would be soluble. So an example, sodium sulfate contains sulfate. Sulfates show up in the top group in our soluble section. Let's get the virtual laser pointer out. So sulfates, there are some exceptions: calcium sulfate, barium sulfate, strontium sulfate, lead-2 sulfate. We don't have any of those exceptions. We've got sodium, and so that means that sodium sulfate is soluble. We also have a group 1A metal in sodium, and there's no exceptions for those, so it's also going to be soluble for those reasons. Any questions or confusion so far about solubility table stuff? We'll do examples. Okay, so these solubility rules are a qualitative description, just saying, yeah, it's soluble, or no, it's not soluble. There's varying degrees of solubility, and this doesn't get into any of that. It's just kind of a general broad strokes rule of thumb, sort of yes it is or no it isn't, and none of the nuance or detail. Molecular solids are not included. This is just for ionic solids. Molecular solids, things like table sugar. Table sugar is polar, and it's soluble in water, since water is also polar, like dissolves like. nonpolar solids like lard and vegetable shortening, both of which are nonpolar, are usually insoluble in water, but you might be able to dissolve them in hexanes or vegetable oil or something like that. Okay, let's use our solubility table. I'll do the first one and then give you the rest to try by yourself. We've got a solubility table up there. You can also use your green sheet solubility table. And we just want to answer, is it soluble or is it sparingly or not soluble? So for our first one, we've got CaS, calcium sulfide. Calcium sulfide has, obviously, calcium. It also is a sulfide. We can find sulfide down here in the sparingly soluble. So initial indication, just looking at that first column of the table, right, we have a sulfide. It's in the sparingly soluble, so we're expecting it's not soluble unless we have an exception. So we check our exceptions, group 1A, 2A, and ammonium salts. We do have a group 2A calcium sulfide. Since we've got an exception, this is soluble. Any questions about reading that table? Okay, go ahead and try to work out the rest, and we'll come back very shortly. Okay, so using our solubility table, we've got iron 2 sulfate. So we have iron and sulfate. We don't have iron in our solubility table, but we do have sulfate. So we're looking for sulfates. So all sulfates shows up in the soluble in water section. And so we're expecting it to be soluble unless we have a listed exception. We do not have an exception for iron. So it's soluble and no exception for iron, meaning that it is still soluble. Next up, we've got lead 2 carbonate. So looking at carbonate, we can find carbonate in our sparingly soluble in water section, so meaning basically not soluble. And our only exceptions would be if we had a group 1A or ammonium salt. So just meaning if we have an ionic compound that's got a group 1A metal or ammonium, is lead a group 1A metal? Does it show up in the first column of the periodic table? It does not. So lead 2 carbonate is insoluble. And we've also got ammonium chloride. Ammonium and chloride both show up in the soluble section of the table. There's no exception for ammonium salts, and for chlorides, of course, we're not going to find an exception for ammonium since it's always soluble. So this is soluble, no exception. Questions about navigating to find any of those? Yes? You would not have to include the no exception part. I just write that to like show you what I'm looking through. Part of the reason that solubility is important is we have some reactions that can form solids out of 2 dissolved liquids. So you may know that laundry detergent works better for cleaning clothes than just like, say, hand soap or dish detergent. And that's because laundry detergent has things in it that help improve its efficacy. So sodium carbonate laundry detergent will react with dissolved magnesium and calcium ions. We've got hard water around here, so laundry detergent having these agents in it is especially important. If you don't have things like sodium carbonate in your laundry detergent, then the magnesium and the calcium can get in the way of your soap doing its job. You might also experience the same thing if you use like shampoo for your hair. Shampoo around here is probably not going to suds up quite as much as if you went like to the Bay Area or somewhere where they have soft water. You'll find that it works a lot differently because of all of those dissolved ions. They get in the way of the soap getting to do its job. So the reaction between the sodium carbonate and dissolved magnesium and calcium ions to form these solids are called precipitation reactions. And our definition for precipitation reactions, or what you should remember, is mixing two aqueous solutions to form a solid. That's a precipitation reaction. And one of the important parts about this is that they're aqueous solutions. It doesn't 100% necessarily have to be aqueous, but they should be dissolved in solution. We've got chemicals dissolved in solution, so we've got clear solutions. They might be colored or not. We mix them together, and when we mix them together, a solid is formed. We saw a precipitation reaction in one of our very early labs, a couple of precipitation reactions in some of our very early labs. And trying to think if we have one. We might have another one coming up in our last lab. But we also have examples in the slides. And the solid is called a precipitate. So this is an example of the result of a precipitation reaction. So potassium iodide solution and lead 2 nitrate solution. If you mix them together, they're both clear liquids, clear solutions, and you mix them together and this really bright yellow lead iodide precipitate forms. This is a very classic example of a precipitation reaction. However, precipitation reactions don't always occur when you're mixing two aqueous solutions. So for example, this image of somebody pouring a bunch of something from a beaker into a bunch of something else, presumably both aqueous solutions. And all we see is bubbles. There's no precipitate being formed. No precipitate is formed. So we're not always going to have a precipitate. Sometimes we will, sometimes we won't. And the solubility table is our key to unlocking whether we have a precipitate that would form or not, if we don't want to like mix the things ourselves. So if we want to predict precipitation reactions, we need to know that precipitates are insoluble solids. Because we're mixing two things that are aqueous, and then a solid is coming out. It's not soluble, so it preferentially forms as a solid rather than staying dissolved in the liquid. So if we have a precipitation reaction, or if we're looking for a precipitation reaction, we are looking to see if we have an insoluble solid that can form. So we might ask ourselves, can an insoluble solid form when we mix two solutions together? If the answer is yes, then it's a precipitation reaction. If the answer is no, then there's no reaction and we've just mixed two solutions together. No big deal. So an example of this in action, when Ki, potassium iodide, and PbNO3, lead 2 nitrate, are mixed, what happens? Before we mix them, they're both dissolved. We know that they're both dissolved because of the AQ, meaning aqueous. So we know they're dissolved, so they're separated out. I'm showing you just one formula unit of the potassium nitrate and 2 formula units of the potassium iodide. I think I said potassium nitrate, lead nitrate. So before mixing, this is what we've got going on. When we mix them together, this is everything that's in solution. So what are some possible combinations of ions? Somebody pick 2 ions that can go together. Ki would be one. What's another possible way that we could combine our ions? Yeah, we could also have KNO3. There's 2 more. Yeah, we could pair lead with the iodide, PbI2. What else? Yeah, lead nitrate is our other option. So these are the 4 combinations that we can have. And the way that we come up with these 4 combinations is we're looking at the positive ions pairing with either of the negative ions. So our potassium can pair with the iodide because they're positive and negative. We can't pair positives together. We can't pair negatives together. We can also pair our potassium with a nitrate. That would be another possible pairing. And we could have potassium pairing up with the iodide. We could also have the lead, I think I said potassium again, the lead pairing up with the nitrate. So this is the 4 possible combinations that we can have when we've mixed these all together in solution. If we look at our initial solutions, there's 2 of those, though, that we can omit. Right? We already know that Ki is aqueous and PbNO3 is aqueous because those were our initial solutions. So we can cross both of those out as ion combinations if we're thinking about precipitation, because we had these dissolved in solution separately. We know that if we combine them together, it's the same ion combinations. Those aren't going to do anything. So the 2 combinations, if we're thinking about precipitation, that we would check are the other 2. So we would check potassium nitrate and lead 2 iodide. And so what happens when we mix those together is that we get the PbI2 precipitating, and the potassium and the nitrate ions remain in solution. And again, the way we would have predicted that is with our solubility table. So let's look at how this might actually play out on an exam or in a lab. A lot of our precipitation reactions are going to be double displacement reactions. So the first step is we know that we've got 2 solutions we're mixing together. For example, like this BaCl2 and the Li2SO4. So we would write the barium chloride and the lithium sulfate. Below the equation, we could write the formulas of the ions. Barium 2 plus, Cl minus, lithium plus, and sulfate SO4 2 minus. This is typically how I proceed for doing double replacement reactions or double displacement reactions. And it's important that we include the charge. We don't need to keep track of what these subscripts do, except for this 4 because it's part of sulfates. Anyway, so write down our ions below, and then we're going to swap the anions. It doesn't matter that you swap the anions or the cations. All that matters is that we're swapping one set of ions. So swapping the chloride and the sulfate, and then I usually write that down below on the right side. So writing out our new combination, Ba2 plus, and not Cl, but SO4, 2 minus. And then lithium now is paired with chloride. So what this does is it picks the other 2 ion combinations, the ones that we don't already have checked, picks our other set of solutions to look at as our products. And then we can crisscross and recombine. And we would get out that our potential products are barium sulfate and lithium chloride. And then we'd go to our solubility table, check for both of those, and see if one of them is soluble, or sorry, if one of them is insoluble. So check if either pair of ionic compounds of ions is insoluble. I think I've got like 3 examples. If both pairs are soluble, you write no reaction. We've just mixed solutions, but nothing actually like substantively happened. If one or both of the new ion pairs is insoluble, then we write the formulas of the compounds after the arrows. If you already have them there, it's no big deal, just cross them out, write no reaction. AQ means soluble, aqueous, and S for solid on the precipitate, the insoluble one. And then the last step for a precipitation reaction is to balance the equation just by changing the coefficients. And we've covered this in the past, but I'll go through the steps again once we've got one that's got a reaction. Okay, for our first example, predict what will happen if aqueous solutions of rubidium hydroxide and cobalt-2 chloride are mixed. Some of you may have noticed immediately that you have no clue what those chemicals are or what the formulas are for those chemicals. You probably recognize chemicals just because not everyone has been keeping up with their nomenclature. So if that was you, take a moment, note, observe. We still need our nomenclature rules. So it's important that we still be able to piece together nomenclature, moving from a name to a formula. You won't always be given the formulas. Okay, so rubidium hydroxide, rubidium Rb, hydroxide OH minus, rubidium is going to be a 1 plus in solution, or as an ion. And cobalt, CO, it's cobalt-2, it's cobalt-2 plus, and chloride, Cl minus. So we would combine those, crisscross them. So our reactants are Rb, OH, and CO, not big O, little o, COCl2. So that's our first step. We've got our reactants. We're told that they're aqueous, so we can add the little AQ after them. Our next step, which we kind of already did as the setup, separate them into their ions. This is just so that we can swap the ions and figure out what our new possible combinations of ions are. So I'm swapping the hydroxide and the chloride. If you want to swap the rubidium and the cobalt instead, that is also fine. Just don't swap both of them. Don't swap both sets of ions because that's the same thing that we started with. Okay, so rewriting these, we've got our Rb plus Cl minus, and these are going to go together. We've also got our cobalt 2 plus with our hydroxide, and these are going to go together. We'll have to crisscross as necessary to get our formula units. So our possible products are RbCl and COOH2. Any questions about how we got there? If the mental math is a strong suit of yours, and you can just do that swap in your head and put the possible products up there, that's fine with me. So you could just jump right to RbCl and COOH2. If that works for you, that's great. So then we go to our solubility table, and we're looking for rubidium and chloride. On our green sheet, chloride shows up in the top section. That's the generally soluble section. And we've got exceptions for silver, mercury, and lead-2. We don't have any of those exceptions, so this one is soluble. We'd write the AQ in front of it. And then for our cobalt 2 hydroxide, hydroxide shows up in the insoluble section of the table. It's the very bottom line for insoluble, except with group 1, ammonium, and slightly soluble with calcium, strontium, or barium. We don't have any of those exceptions. So this is insoluble. We put an S behind it, meaning that it's soluble. So we do have a reaction. If we mix these two solutions together, we would expect to see cobalt 2 hydroxide form as a solid. Questions on the new stuff, the stuff we've just talked about on this slide? Okay, then the last step is to go through and balance the whole thing. So the way that I like to do double displacement reactions, we look for something that's different on both sides. So rubidium, for example, is 1 on both sides, so we're not going to touch that. The only thing that's got a 2 on the left side is the chloride. We've got a 1 for our chloride on the right side, so let's start with Cl. We've got 2 on the reactant side, 1 on the product side. In order to get those balanced, we can add, I'll switch to purple, we can add a 2 in front of rubidium chloride. So now our chlorides are balanced. When we balance the chlorides on the right side, we also changed our rubidiums, so we're going to balance rubidium next. So Rb is up next. We have 2 on the product side, and we currently only have just this 1 on the reactant side. So we're adding a coefficient of 2 in front of RbOH. When we changed this, added this coefficient of 2, that also affects our hydroxide, so that's what we'll balance next. We've got 2 on the reactant side because of the 2 coefficient in front of RbOH. We have a subscript of 2 on our COOH2, meaning that we have 2 hydroxides. So that's already balanced. And then we would check the last thing, our cobalt. We've got 1 cobalt on the reactant side, 1 cobalt on the product side. So our cobalt is balanced. We're done balancing. All right, predict what happens if aqueous solutions of strontium bromide and aluminum nitrate are mixed. I'll give you a little bit of time to work out what those are and write out the products of the reaction. All right, so strontium bromide. Strontium is Sr2+, Br is bromide. It's got a 1-, so it's SrBr2. This is aqueous. The problem tells us so. Our other reactant is aluminum mixed with nitrate. Nitrate, NO3, is a 1- and aluminum is a 3+. So we get AlNO33, also aqueous. Add in our reaction arrow. And then to figure out what our products are, we deconstruct our reactants and we swap either the positive ions or the negative ions, not both. So the way that these will recombine as possible products is the strontium will be paired with the nitrate, and the aluminum will be paired with the bromide. And we have to crisscross where necessary. So our products, possible products, are SrNO32. We don't know if that's aqueous or solid. And AlBr3. Again, we don't know if that's aqueous or solid. If we do have a reaction, that's what our products would be. And then we go to our solubility table. Before we do that, any questions about how we got here? Okay, going to our solubility table for strontium and nitrate. Nitrate is in the second group of our soluble, so the top section, the second line. NO3- is there. There's no exception. So it's soluble with no exceptions. So that would be aqueous. Now we have to check our aluminum and our bromide. Bromide shows up in the top section, so it's in our soluble. It's the third line down, Br-. Br- is also soluble, except with silver, mercury, and lead 2+. So this is also soluble. So we would write no reaction. We had some salty water and we mixed them together, and it's just a combination of the two salts, but no solid was formed. That will happen occasionally. All right, one for you to try all the way through. Write an equation for the precipitation reaction, if any, that occurs when solutions of potassium sulfate and lead 2 nitrate are mixed. If no reaction occurs, write no reaction. Okay. we are looking for the precipitation reaction between solutions of potassium sulfate and lead 2 nitrate. So K2SO4 and PbNO3 When we turn those into products, break them apart, swap the ions, recombine them, we're going to get KNO3 and PbSO4 as products. If we go and check our solubility table, we'll find out that KNO3 is soluble, no exceptions. It's got potassium in there. Then when we go and look for our lead 2 sulfate, sulfate shows up in our soluble section. However, we have an exception. So we have an exception with Pb2+. So it's solid. Rather than being soluble. So we do have a reaction, and then the last step would be to balance it, and all that we need to do here is add a 2 in front of our KNO3, and that will get it balanced. I'm rushing it so that we can hopefully start to catch up on lecture a little bit. I forgot how far behind we are. Questions about that example? Okay, other things that we can do with reactions that happen in solution. There's 3 types of equations that we can write out. We have been looking at the molecular equation. The molecular equation shows the complete neutral formulas for every compound in the reaction. In the book, I believe this is often called the complete chemical reaction. So this is what we've been looking at. So this is what we are used to seeing. It's what's familiar to us. However, we can also write a complete ionic equation, so showing the ions in solution. So showing the ions as they exist in solution. So anything that's got AQ after it will separate into ions. And it's our complete ionic equation because we're still showing everything. There's another form of this, another type of ionic equation that is not complete, and that's called our net ionic equation. So our net ionic equation down here at the bottom removes spectator ions, and spectator ions, as the name sort of implies, spectators at sporting events spectate, they watch, they don't do anything really. Like there's obviously some effect to clapping and cheering that comes out of fans being there, but you can still play the game even if there's nobody there. And our spectator ions in the same fashion are ions that are unchanged, they only watch. So they're unchanged on both sides of the equation. So if it shows up on the left side, shows up on the right side, and nothing is changed about it, that's a spectator ion. We can, if need be, throw those spectators out and pare it down, P-A-R-E, it down to the net ionic equation. And this shows only the species, only the chemicals, only the ions, only the molecules that actually participate in a reaction. This is a summary slide. if you want to refer to that later. Okay, so we have a reaction that occurs in aqueous solution. We've got everything written out already, so we're skipping past separating the ions, swapping them, recombining them, checking our solubility table. We're assuming that we've already done all of that. This is our complete molecular equation. We want to write out a complete ionic equation and also a net ionic equation. So we're going to separate everything out into its ions if it's aqueous for our complete ionic equation. So our barium chloride, we've got 1 barium, 2 chlorides. It's aqueous. So we've got Ba2 plus, 2 Cl minus. Our sodium sulfate, Na2SO4, we've got 2 sodiums, and we've got 1 sulfate, SO4 2 minus. So that's our reactant side broken down. On the product side, barium sulfate is a solid. So we're going to show that as BaSO4. I'm going to write the S behind it just so we know that it's solid. And we've also got 2 NaCl. So 2 Na plus and also 2 Cl minus. So this is our complete ionic equation. We want to get now our net ionic equation. Which chemicals were the same on the left side, on the reactant side, as they are on the product side? Na, right, we've got Na plus on the left side, we've got Na plus on the right side. It didn't do anything. We've also got Cl minus on both sides. So we're going to remove the Na plus and the Cl minus to make our net ionic equation. It was the barium and the sulfate that actually went on to produce something new. Everything else is just unnecessary spectators. So Ba2 plus SO4 2 minus goes to BaSO4 as a solid. Questions about our equations there, how we got them? All right, that'll do it for this chapter.